When designing an electrical substation, it's crucial to properly account for intermittent application motors. The National Electrical Code, commonly referred to as NEC, defines intermittent duty motors as those used for short periods and not continuously rated. While the NEC doesn't provide a specific formula for handling these motors in substation design, it offers guidance for determining their operating capacity. A common method is using a demand factor. This factor is a multiplier applied to the motor's nameplate rating, acknowledging it won't run continuously. The appropriate demand factor varies with the motor type, its application, and duty cycle. However, a general rule of thumb suggests a demand factor of 0.75 to 0.85 for intermittent application motors. To incorporate these motors into your substation design, apply the chosen demand factor to each motor's nameplate rating. This gives you a reduced load capacity for sizing substation equipment. For instance, a 50 horsepower intermittent motor with a 0.75 demand factor yields a reduced load capacity of 37.5 horsepower. You then design for 37.5 horsepower instead of 50 horsepower for that motor. Remember to also consider all other loads connected to the substation, such as lighting, heating, ventilation, and other equipment. The substation equipment should be sized to handle the total load of all connected devices. Let's delve a bit deeper into how to apply these principles. Firstly, collect the nameplate data of all intermittent motors. This data will provide all the details. Secondly, determine the appropriate demand factor. Factors like motor type, application, and duty cycle all play a role. Consult relevant tables or guides to get this value. Thirdly, multiply the nameplate rating of each intermittent motor by its demand factor. This gives you the adjusted load for each motor. Fourthly, sum the adjusted loads of all intermittent motors. This is the total intermittent motor load. Fifthly, calculate the continuous load from the 150 motors with continuous application with an approximate load of 640 kilovolt amps. Convert the kilovolt amps to horsepower if needed, using appropriate conversion factors. Sixthly, add all continuous loads and intermittent load. This is the total calculated load. Seventhly, factor in any additional loads, such as lighting or other equipment, and add this to the result from step 6. This is the total load the substation must handle. Eighthly, select your substation components, such as transformers, switchgear, and protective devices, based on the total load. Consider a safety factor to accommodate future growth. Ninthly, verify that your design complies with all applicable electrical codes and standards, including the NEC. Tenthly, document all calculations and design decisions for future reference and maintenance. In NEC Table 430.150, you can find the full load currents for 3-phase motors. This table is essential for calculating the current draw of motors, which is necessary for sizing conductors and overcurrent protection. The NEC provides detailed guidance on motor circuit protection, including overloads, short circuits, and ground faults. Article 430 covers motor circuit conductors. The conductors must have an ampacity sufficient to carry the motor's full load current, increased by a certain percentage for motors used in continuous operation. Specifically, NEC Section 430.22 addresses the size of conductors feeding a single motor. It dictates that the conductors supplying a single motor used in a continuous duty application must have an ampacity of not less than 125% of the motor's full load current rating. This 125% factor ensures the conductors can handle the continuous load without overheating. The full load current rating is determined from NEC tables 430.247, 430.248, 430.249, and 430.250. For intermittent duty motors, Section 430.22 exception allows for some adjustments. The conductor ampacity can be reduced based on the duty cycle of the motor, as long as it is sufficient for the application. For multiple motors on a single feeder, NEC Section 430.24 provides guidelines. The feeder conductors must have an ampacity of not less than 125% of the full load current rating of the largest motor, plus the sum of the full load current ratings of all other motors in the group. This ensures the feeder can handle the starting current of the largest motor while also supplying the other motors. Article 430 also covers motor overload protection. This is designed to protect the motor itself from overheating due to excessive current draw. NEC sections 430.31 through 430.40 provide the requirements for overload protection devices. Overload protection devices are typically thermal overload relays or electronic overload relays. These devices are designed to trip and disconnect the motor from the power supply if an overload condition occurs. The size of the overload protection device is based on the motor's full load current rating and the service factor of the motor. For motors with a service factor of 1.15 or greater, the overload protection device can be sized at 125% of the motor's full load current rating. For motors with a service factor of 1.0, the overload protection device must be sized at not more than 115% of the motor's full load current rating. Short circuit and ground fault protection is another critical aspect. These devices protect the motor circuit from high current faults, such as short circuits and ground faults. NEC sections 430.51 through 430.58 provide the requirements for short circuit and ground fault protection. These devices are typically fuses or circuit breakers. The size of the short circuit and ground fault protection device is based on the motor's full load current rating and the type of motor. The NEC permits the use of inverse time circuit breakers or fuses for short circuit and ground fault protection. These devices have a time current characteristic that allows them to carry a short-term overload without tripping, but they will trip quickly under high fault current conditions. When selecting components for your substation, it is essential to consider the continuous and intermittent loads. First, determine the total continuous load of your substation by adding up the loads of all continuously operating equipment. Second, determine the total intermittent load of your substation by adding up the loads of all intermittently operating equipment, factoring in the demand factor. Third, calculate the total apparent power. This is the square root of the sum of the squares of the real power and the reactive power. Fourth, determine the required transformer capacity. The transformer must be sized to handle the total apparent power of the substation. Fifth, size the switchgear. The switchgear must be sized to handle the maximum fault current available at the substation. Sixth, select protective devices, such as circuit breakers and fuses. These devices must be sized to protect the equipment and conductors in the substation from overloads and short circuits. For motors with variable frequency drives, or VFDs, there are special considerations. VFD allow for precise control of motor speed and torque, which can improve efficiency and reduce energy consumption. However, VFD can also introduce harmonic currents into the power system. These harmonic currents can cause problems with other equipment in the substation, such as transformers and capacitors. To mitigate harmonic currents, harmonic filters may be required. These filters are designed to reduce the amplitude of the harmonic currents and prevent them from propagating through the power system. The NEC also provides guidance on the installation and wiring of VFD. Section 430.130 addresses VFD. It requires that VFD be installed in accordance with the manufacturer's instructions and that they be properly grounded. It also requires that the conductor supplying the VFD be sized to carry the VFD input current. Grounding is extremely important. Proper grounding is essential for the safe and reliable operation of the substation. The grounding system must be designed to provide a low impedance path for fault currents to return to the source. This helps to prevent electrical shock hazards and equipment damage. NEC Article 250 provides the requirements for grounding electrical systems. It requires that all metal enclosures and equipment be grounded and that the grounding electrode system be properly sized. The grounding electrode system typically consists of a ground rod, a ground plate, or a metal water pipe. The grounding electrode system must be connected to the neutral point of the electrical system. Documentation is critical. Thorough documentation of all design calculations, equipment specifications, and installation procedures is crucial for the long-term maintenance and operation of the substation. This documentation should include single-line diagrams, wiring diagrams, equipment schedules, and test reports. The documentation should be kept in a safe and accessible location. Regular inspections and maintenance are also essential for ensuring the safe and reliable operation of the substation. Inspections should be performed regularly to check for any signs of damage or deterioration. Maintenance should be performed in accordance with the manufacturer's recommendations. This may include cleaning equipment, tightening connections, and testing protective devices. By following these guidelines, you can ensure that your substation is designed and operated safely and reliably, accounting for both continuous and intermittent motor loads.